Okay, dear student, let us see what is there in this question. Describe the quark structure of a baryon. And this question is going to fetch 2 marks for you. Definitely, it just needs a simple kind of description for the baryon. So we can clearly say that baryon is consisting of 3 quarks. There is no antiquark there. Simple. I don't feel there is any other need to say anything. Let us see what is there in the mark scheme. Okay, so here 3 quarks. Example with the 3 quarks and example up down. You can give an example for the proton and the neutron. The baryon number is 1 by 3. The baryon number overall, it is like, you know what to write here, isn't it? Let us go for the next question now. The Feynman diagram shows a possible decay of the K+meson. So the K+meson is there, and we are talking about a possible decay here. Okay, fine. A possible decay means there could be any other kind of decays also, but this is shown here. Identify the interactions that are involved at the point A and point B. So we want to talk about the point A and point B, and we have to comment on what kind of interaction is that. So how many interactions do we know? Number one is weak interaction, weak nuclear interaction. Number two, strong nuclear interaction. Number three is electromagnetic interaction that only occurs when there is a like electron and a proton, positive and the negative charges. And what is the fourth type? Is there any fourth type? Gravitational. So we don't talk about the gravitational interactions at all. Um, it is not even electromagnetic interaction. We are left with two: weak interaction or the strong interaction. W plus is there at the point A. So my dear students, there are a couple of things that we have to note here. Number one, when the strange quark is involved and the strangeness number is violated in a reaction, here clearly the strangeness is +1. Strangeness number is -1 for the strange quark and +1 for anti-strange. So after that, there is no strange available here. It means that strangeness is violated. So clearly it is going to be a weak interaction. Strangeness is violated. Point number two for the weak interaction is to identify the weak interaction. Whenever there is a boson like W minus boson, W plus boson, and Z0, well, according to our books, they say that Z0, W plus, and W minus, whenever they are involved, that interaction is a weak interaction. So W plus is also given there. So clearly, A interaction is a weak interaction, nothing more. So we know about that. So this is a weak interaction at A. What about B? Now, B is a strong interaction because gluon is involved there. So for the strong interaction, either the gluon or a meson will be involved there. So in this case, clearly a gluon is there. So A is a weak interaction, B is a strong interaction. Nothing more in this horrible Feynman diagram that I will say, because like there are very less number of examples for the Feynman diagram that are given in the books, which are concerned with the the mesons. But anyways, so this is what is our answers here, and I think nothing more than that, because it is going to fetch 2 mark for you, so they do not want anything more than this. So this part is clearly over. Let us now move to the next. K+meson can decay as as this also. So this is also a decay which was for K positive. This is also K positive. So this is another kind of reaction, possible reaction that they have shown here. So let us try to analyze what is this now. State and explain the interaction that is responsible for this decay. State and explain the interaction. So first of all, you have to comment on like what kind of interaction is this, strong or weak or what, and you have to explain it. What is happening here is, this is a meson. Clearly there was one strange, anti-strange, and the other was up. And on the right hand side of this reaction, I can clearly say this is neutrino, and this is muon, which is lepton. So both of these are lepton. Lepton number is conserved. So this is a particle. So the lepton number here is +1. Here this is muon positive, which is the antiparticle of the muon negative. So for this, the lepton number is -1. So lepton number is conserved here. So it means that the meson is converting itself into leptons. It's a very strange phenomena that is written on your screen. The quarks have been completely vanished. The quarks are no longer present on the right hand side of the equation. It means that the quarks have been completely destroyed, and only leptons are left. So it's one such nuclear reaction. Obviously, this is going to be a weak interaction. Why? Because quarks have been destroyed. Also, the point number two, it is involving a strange antiquark. As I have already told you, that whatever be the nuclear reaction, if strange quark or anti-strange is involved, definitely that interaction is going to be a weak interaction. Is it okay? So our answer here will be a weak interaction, and you can explain it. So this is the answer here. Let us see. Yes, the weak interaction. Strangeness is not conserved. Um, Exchange particles are there, but they are not shown here. Neutrinos are only produced via weak interaction, but yeah, you can even say that. So these are the explanations that they have given. I have also given you the explanation, so you can just write it, and we can say that yes, this is going to be weak interaction. So this is how we are going to give the answer for that. This was the last question for the question number 5. So my dear students, thanks for joining. Please share my video. All the best.